Okay, so one more thing about, I guess, my teaching philosophies. I'm going to be big on this the first couple of days because, I don't know. I think I've been told I'm going to teach probably differently than you're used to in science. Like, I'm very different than, say, lab. I'm also fairly different in math as well as in teachers you've had. So it might take a little while to get used to my style of how I teach, but one of the things that I firmly believe is that I do not want you wasting all of your time writing down notes by hand. I think that is the biggest waste of time. I also do not see a lot of purpose in it. And it's not a skill that I see gets extrapolated to other places in life all that often. I mean, occasionally, yes, it's important to be able to write stuff real fast, but that's not my goal here. So my goal is to give you guys all of the information on my slides up ahead of time. Does that make sense? Now, there's a trade-off here. I found, and I think if you've talked to students who I've had previously, not that I'm skipping on putting information here, but what you really need to do is write down what we talk about. Does that make sense? Oh. An important skill is not to be able to regurgitate, but to be able to be part of the classroom discussion as we talk about things. Occasionally, like say there'll be like a math problem where we'll have to do some work together, right? But that's our goal is I'm not going to, one of my biggest pet peeves, and I hopefully will do this very little, is a person who gives a presentation and they do this. Elements. The components of all matter can be separated into building blocks called elements. There are now... I see no value in that. You guys can read. Does that make sense? So very often I will be like, you guys can read that slide, now move on. Does that make sense? So if you have highlighters, some kids sometimes find that to be useful. Because if I seem to feel like it's worthwhile that I actually point something out on the slide, then it's worthwhile for you to highlight. So that's one of my goals. Don't write down what's up there, write down what we talk about. So let me go back to my first slide here. We're going to review chemistry from what you guys learned in grade 10. And I would think in grade 10 you guys probably would have learned periodic table. Is that right? Although maybe your memory's a little bit sketchy, like I gave some examples before. If I gave you CuCl2, you might have been asked, name that thing. Make sense? Like if I write it out here, maybe I'll write it out. If I said CuCl2, is that something that maybe rings a bell, or it's like, maybe you don't know the answer, but like you recognize, yes, I should have known the answer to something. Does that make sense? Anybody know what this is called? What was that? Very close. It's actually copper 2 chloride. You have to put a Roman numeral in the middle of it because of the fact that copper has more than one valence state. But copper chloride is basically as close as you can get. One more thing that you guys might have gotten to, depends on how far lab gets, is, I think I kind of said this before, if I give you ClCl2 and we add, I don't know, NaOH, then I might ask you, what's this going to make? Did you guys do stuff like this at all, where you had to predict stuff? No. And then the answer to this one would be that you're going to make CuOH2 and NaCl. And then sometimes you have to do one more step on top of that. You have to balance an equation. If you like the analogy that I gave earlier of chemistry being a language, balancing is like punctuation. Like using capital letters or using a semicolon in the right spot. I mean, is this equation wrong? Well, no. I mean, I guess it's kind of right. But it's not fully balanced because on this side of the equation right here, you have 2 chlorines. And on this side of the equation right here, you only have 1 chlorine. So like grammatically, chemistry E. Does it make sense? So like you'd have to put a 2 here and 2 here. Does that make sense? And I gather that pretty much would have been 2 months of chemistry, what I just described there. Is that about right? Okay, my goal, we're going to go through all of that in less than 2 weeks and try to refresh your memory on that before we move on. Sound good? Yep, cool. Okay, first question then. What is chemistry? Anybody know? Like if I asked you to define chemistry as a word, what is chemistry? I'm asking for participation here. Devin, you're on the spot. Okay, that's good. I like the word producing. Sometimes I use a different word instead of producing. Anybody want to take another shot at it? That was a good one, by the way. Please don't be scared. I'm not scary. I won't yell at you or make fun of you or... Someone be brave. It's a good word. Can you put it in a sentence?
Elements react with each other.
Does it have to be elements? hold on that thought. The thought is that it has to be elements. Because, I mean, in chemistry we talk about elements. Okay, let me give you an example. My car starts to rust. Is that chemistry? Sure. Is my car an element? I mean, it's made of elements, sure, but I mean, I don't think it's really fair to call my car an element, unless actually it was the brand element. What was that? Okay. It's a different word we use. We sometimes use the word matter. Maybe this would be a good example, by the way, of something to write down. Anybody know what matter is? Really good there. Okay. Before I get to that, most often you actually pick the answer that I wanted. Most of the time when I ask someone what matter is, the best definition someone can give me is stuff. Matter is stuff. You are matter. You're made of stuff. But, I mean, if we want to give a more technical definition, what did you say again? Yeah, matter is defined by two things. One of the things is that it occupies space. So chemistry involves matter, stuff that takes up space. There's one more thing to matter, though. Anybody happen to know the other half of it that makes something matter? Nice, good job, yeah. Matter has to have mass, so it has to weigh something. Matter has to have two characteristics. Matter has to take up space, and it has to weigh something. It has to have some sort of girth to it, I guess. Does that make sense? An example of something that does not matter would be like deep space, like outer space. You guys ever heard the term vacuum? Not like vacuum cleaner, but like vacuum in a science sense. A vacuum basically is like where there's space, but like literally there's nothing in that space. For example, I have a vacuum sealer that I use to like, when I go buy like steak at Safeway, and like we put it in the package and suck all the air out. You guys know what I'm talking about? One of those things, right? And as a vacuum, what it's doing is it's trying to remove all of the air. Make sense? Right? I mean, the steak stays behind, right? But let's say you had a jar and you sucked all of the air out. What is inside the jar? Well, there's still space there. I'm using my fingers, right? But is there actually matter inside there anymore? So matter is something that takes up space and has a mass to it. And then you used the word produces, I think, earlier. Sometimes in chemistry, maybe a better word to use would be the word changes. Maybe not so much produces. Produces is a good synonym, I guess. But the definition of chemistry is the study of how matter changes. That's what we're going to talk about. We're going to talk about how stuff becomes other stuff. We don't live in a stationary world where something just stays still the whole time. We live in a world where stuff changes, right? And sometimes the changes for the better. We're going to talk about so many different examples, but let's say combustion. We're talking about a car. Inside your engine, gasoline burns, and basically it blows up is what happens, right? And that was a useful process because it helped make your car go. That's a change. Anybody know what the byproducts of that change are when you combust it? CO2 and water are the byproducts of that change. That's a positive change. Well, not the CO2, I guess, but like combustion in your car, that's a useful thing, right? Whereas I mentioned rusting a little bit earlier. Rusting is also a chemical change where iron turns from like a pure iron into like an iron oxide ore kind of compound. And then it flakes off your car, and then your car starts to turn that orangey kind of, you know what I mean? That's not a positive change. So, anyways, the first thing I want you guys to know is what chemistry is. Our goal is to study matter, and that's where we're going to start. We're going to talk about how to name matter, so NaCl, sodium chloride, CuCl2, copper 2 chloride. And then once we figure out how to properly name this matter, then we're going to talk about all the different ways that it changes. Does that make sense? So, first half of that goal, then, we got to talk about how to name matter. And so we're going to start off with the basic building blocks of life, our elements. Okay. So you guys have some experience with the periodic table, I gather. So basically the idea here is that all of the matter, there's that word again, volume plus mass, are elements. Many of them are naturally occurring. There are some synthetic ones. Do you guys have any idea how to figure out which ones are synthetic or not? Okay. As a general rule of thumb, synthetic things are kind of man-made. This is not the best periodic table for this, but like you see how like these guys are black right here, and then blue, and then red, solid, liquid, gas. usually these ones that are white or synthetic, as a general rule of thumb. So it's usually like these guys, the crazy ones down here. Yeah. On your periodic tables, though, if you can't see that one, you guys find your data booklet thing here. On your periodic table, as a general rule of thumb, if you want to try to find a synthetic element, synthetic means that it was like man-made and developed. We're not ready to talk about molar mass yet, but there are numbers on these things here. Yeah, let's find one here. You guys find hydrogen, like literally the first one up in the top corner there? Hydrogen has a molar mass of 1.01. That's how much it weighs. And technically it's an average weight, and we'll get to that. But if it has like 2 decimal place numbers, it's probably naturally occurring. However, if you go all the way down that row down to francium, number 87, see how the 223 is in brackets? That's a good indicator that francium is likely a synthetic compound. Okay? That makes sense? And one of the reasons why for that is that it does not have like an average molar mass because it probably has to get developed in the lab, or it's a byproduct of, say, a nuclear decay of some kind. So as a general rule of thumb, if you're looking for a synthetic element, look for the ones that have the little brackets around the molar masses. And those ones are probably going to be synthetic. There's probably some gray area in there, but for our purposes, that's how you'll tell the difference. Does that make sense? Cool. Thank you for saying yes, by the way. Okay, hopefully you've known some of this stuff before. Your periodic table is roughly divided based on so many different properties, but one of the first ones is metals versus non-metals. Everything on this half of the table is usually black. And black means solid. And I gotta point out one of the first things you need to know. Solid does not mean metal. Yes, solid things are usually made out of metal, or metal things are usually solid. But that's actually not like how we're defining metals. Okay. So there's a little staircase line on the periodic table. You guys know this? Like this little line right here? Is this something you guys know about? Okay, so basically if it's on this side over here, it's considered to be a metal. And if it's on this side over here, it's considered to be a non-metal. And if it's like right on the staircase, it's kind of like an in-betweener, and we call it a metalloid. And only a few things fall into that metalloid category. But the most important thing I need you to know is that metal does not mean solid, because there are exceptions. For example, over here, this guy right here would be hydrogen. Hydrogen is on the metal side of the table, but it is not solid. Hydrogen is a gas. That makes sense? Mercury is like roughly right about here, and mercury is usually a liquid. We still call it a metal. Does that make sense? Don't we? Moving on. I guess you guys should know some of the properties of metals, actually, before I get to that. Most of these words you probably know. I would say most of the time people don't know these two words. So we should maybe talk about those two. Does anybody know what malleable means? Nope, that's like a semi-permeable membrane, maybe is what you're thinking. You had an idea? Yeah, usually malleable means that you can pound it into a sheet of metal. So like shaping it's a good example, but I would say like you can make it into a sheet. So like a strip of aluminum, for example, you can pound with a hammer, right? Even like bend or shape, that's actually a good way of putting it. You can bend or shape it. Anybody know what ductility refers to? Actually, no. No. Ductility refers to the ability to be pulled into wires. Something along those lines. Like it can be stretched and pulled into a wire. Like for example, copper is a very ductile substance. Because I can make wires out of copper. And like if I pull on it, it's not going to snap. Does that make sense? So like the way I remember it is malleable means like I think of a sheet of aluminum. I can bend it into, I can hammer the sheet of aluminum, right? But I mean, it may also have the property of being able to make and turn into a wire. It may not. So, non-metals are basically the opposite. So if something is not ductile, it means that it can't do this. So, metalloids are exceptions, and you guys should just write them down on your periodic table at some point, just so you know which ones they are. But they're basically all the ones that are on that little staircase line. So, moving on. I gotta keep going here. Do you guys know the terms groups? Basically, up and down. So there's 18 groups. A few of them have special names. Alkali metals are like the hydrogen lithium group. Beryllium is the alkaline earths. Noble gases are the very, very end, and halogens are right before them. Is that something you guys have heard before? Okay, I'm going to move on then, because I hate going over things, you know. Periods go this way. And there's basically 7 periods in the periodic table, which seems odd, because some people look at periods and they go, hey, there's 1, 2, 3, 4, 5, 6, 7, 8, 9 rows. There's 9. You guys know how like this bottom row here is actually like supposed to slot in that little slot right there? Have you guys been told how that works before? Like if you look at the numbering system, it goes 56 and then it jumps to 72. Because it's actually supposed to go 56, 57, 58 through there. And we make our periodic table like this to save room. Because otherwise, if you put all of those chemicals right in there, it would make the periodic table even longer across. And that would be ridiculous. So there are only 7 of them in terms of how many periods there are. Okay, other things. Often? No, not often. Almost. I'm going to ask you guys to write, after you write a chemical, to write a state of matter. Like, you know how you put like a little S afterwards something? It means it's solid. If you like the analogy of how learning chemistry is kind of like learning how to read and write again, this is like punctuation. And I consider it to be very important to put proper punctuation. So you know how I wrote copper beforehand? I would consider this not to be a correct answer. You should really write copper solid. So then there lies the question, well, how will I know? Okay. Well, if it's an element, look on your periodic table. Okay. And I know your guys' ones here aren't in color, but I mean, look at this one if you need to. Copper is right here, it's black, so it's solid. Does that make sense? Okay. There are a couple of odd chemicals, though, when they're by themselves. And we call these things the allotropes that they have. Hydrogen and nitrogen and oxygen. Have you guys seen how like they come in groups of 2? Is that something Lab might have explained before? Some things come in groups of 2. They're called diatomics. Sulfur will actually often come in 8s. Phosphorus will often come, I believe it's in 4s. Might be 3s. And carbon can sometimes come in a whole bunch of different possibilities. Sometimes it can come in like 20. And so sometimes we have to write like a small little number afterwards, letting you know how many they come in groups of. But for sure the ones you need to know are the diatomic ones. So that's hydrogen, nitrogen, oxygen, fluorine, bromine, iodine. Basically, it's all of the ones around the corner right here, and then hydrogen. So make sure you don't forget the little 2 afterwards if there has to be one there. Again, it's like punctuation. It's like forgetting a capital letter. And don't forget state of matter. It does make a difference sometimes. So speaking of showing states, make sure you do that for elements, but also for compounds. Do you guys know the difference between an element and a compound? Here's an element. Here's a compound. You 2 of them together, right? So compounds are a bit trickier. So as a general rule of thumb, if it's ionic, it's probably solid. Do you guys know the term ionic? I got it on further slides here in case you don't. But an ionic thing is where it's a metal and a non-metal. Okay. Whereas if it's a molecular compound, usually as a general rule of thumb, if it's a small molecular compound, like see how CH4 only has like 5 total elements in it? 1 plus 4 is 5. It probably is a gas. Whereas like gasoline that you put into your car is C6H14, so there's like 20 total things there. 6 plus 14 is 20. It's probably a liquid. What, gas in your car is a liquid? Whereas like if you were to use like beeswax, like honey is molecular, but usually it's in like a solid type format, and that's because it's really big molecule. Long story short, I want you guys, every time you write down a chemical or a compound, to put a state of matter afterwards. Now, most of the time, if you get it wrong, I don't care. Okay? Like, if you say that it's solid, but maybe it actually should have been a liquid, I'm not going to dock you marks, but I do want you to get in the habit of trying to write the state of matter afterwards that it should be, because it makes a huge difference. Because sometimes it's okay for it to be a solid, but it's not okay for it to be a gas, for example. Does that make sense? Hopefully you guys know these words, physical and chemical changes, because here's kind of the second half of that chemistry definition. We're going to want to talk about how stuff changes. So physical changes are where you don't actually change the chemical formula at all, and chemical changes are where you do change the chemical formula. So like freezing, for example, doesn't change anything. You guys know this? This is kind of a boring review. Let's move on to something more challenging. Okay, just so they can find this slide here. Are elements as small as things can get? No. Elements are made of what are called subatomic particles. Hopefully you guys have heard these before, right? There's the protons, neutrons, electrons. So protons are positively charged, electrons are negatively charged, and neutrons have no charge. Does that make sense? So one of the first things that I'm going to ask you guys, like where we can actually now do something, is if we talk about like an element, we want to try to figure out how many protons, neutrons, or electrons it has. Okay. Here's the first thing I need you guys to know. If we ever talk about atoms, atoms are always neutral, which means your protons and electrons have to be the same. So if I talk about a hydrogen atom has one proton, has to have one electron. Okay. Anybody know the opposite of an atom? It's called an ion. I know I have it on another slide here, but an ion is where protons do not equal electrons. And what ends up happening is that an ion has charge to it. Make sense? If an atom has to be neutral, and there's 5 pluses and 5 minuses, it balances, right? But if there's 5 pluses and 4 minuses, well, now it's an unbalance. So things that are unbalanced are called ions. So I want to make sure you guys have that terminology correct. Atoms are neutral, ions are charged.
Please excuse the interruption.
Time here.
Here are a couple of announcements. All FMNI support